All right. Now the next one is 6.9. This section is actually now considered the case. The field actually exactly single frequency, and for natural phenomena, it's very difficult to have a pure sinusoidal or purely oscillatory field. But for a control experiment like a circuit or application, so you can try some circuits through some kind of a oscillatory driver, like whatever it's like ordinary AC circuit. They try some whatever some application, some circuit. Then you can try using a single frequency, just zero. And say, for example, this is an antenna, then you have you produce electric field, right? And then you can also talk about conservation of energy in this situation. And so the treatment different from this first medium is that now we don't have this. We don't even talk about this epsilon and mu depends on omega. It's just everything is single frequency. Then the original problem in the equation that we just cited, the 6.105, because it's total frequency, that you can actually substitute the dt to minus I omega and get rid of the problem that we said is problematic unless you have relationship between E and D and it can be. But for a pure single frequency, that you don't have that problem. And now another thing to learn from this section is how you take the time average of a product. So you have electric field or magnetic field or whatever field that is in single frequency or oscillating. But sometimes you consider a product between two of these oscillating fields. And the idea is that then you take the time average, just like over here, and you will get something that independent of time. So so that is something is needed for the Poynting theorem because in Poynting theorem obviously you have products. You have the J dot E, and then also you have the energy density, both products of two. Those are like quadratic term. You have E dot E and H, that kind of thing. So then first you will need to discuss what it means by when you have single frequency field, what the product will look like. So that will require some complexity again, but we'll figure that out. So now everything is single frequency. The injection notation is like you have spatial dependence, like electric field spatial dependent, and then you have a single frequency, and it's much more convenient to use exponential function for single frequency quantity rather than using sine and cosine. And the reason is the derivative is of this thing is will give you the itself, the function itself. But for sine and cosine, you take the derivative of sine, you get cosine. Take the derivative of cosine, you get back the sine or negative sine, right? So that you're mixing sine and cosine and make the equation complicated to solve. I mean, it's not impossible, but it can sometimes lead to confusion and error. So it's much easier to use complex notation. Okay, so if you are not familiar with complexing, and the first thing you remember, the introduction of a complex number or complex function is to help you, not to give you extra trouble. Okay, so learning this thing is useful. because otherwise, if you stay with sine and cosine, you pretty soon find yourself in much bigger trouble. Okay, so the idea is that this is to represent the electric field with a single frequency represented by this exponential function. But the convention is that the field actually just use the same notation of E, so it doesn't change the notation, but this depends on X and T in the argument. So what is implicit means is that you take the real part. So usually we ignore this notation and we write it like that, is assuming that we're taking the real part anyway. But if we want to be explicit, we can add back this notation, taking the real part of that. And another way to write down the real part is that this is equals to 1/2 of the original term plus its complex conjugate. That is what it means by taking the real part. Is that okay? So you all of you remember this one? A complex number plus its complex conjugate divided by 2 is its real part. Okay. So now we assume every term, every quantity is like that. And then we talk about a product. Say E is like that, and then J would be the same. So now we talk about J dot E. That is the work done to the particle, or the whatever in the circuit would be the whatever the current, the material, right? And now again, so this is this E, and then you have a corresponding J, so similar to that. So what it means is we take one. Each one has this similar expression, so that altogether is 1/4 J x to the power minus 1 into T plus J complex conjugate. So when all this quantity with just the spatial dependency, that can be complex, so that therefore we can take a complex conjugate. Yeah. It's okay to I mean, just using the same notation sometimes will cause confusion. So this is will, right? This is will, but this is complex. This also can be complex. The electric field with only when we have this expression, this can be complex. And the reason is that we are writing is this single exponential function. Exponential function has a sine and cosine. The real part is cosine omega t. The imaginary part for this minus one is minus sine omega t, right? So we're actually combining the sine term and cosine term in a single expression. And when you take the real part, you're taking the real part of electric field, this electric field times the cosine one, plus the imaginary part of this one times the sine one. Maybe there's a negative sign before you take because I times I is -1. That will give you the real part. Okay, so therefore, in general, this is compact. It has its own real part and imaginary part. The physical meaning is just the real part will go into cosine term, the imaginary part will go to the sine term. But we don't write it as so generally, if you don't use complex notation, you will write two terms in here. There'll be a sine term, there'll be a cosine term, or alternatively, you can write a cosine plus omega t plus a phase. That is another way to write the sine term, because you know that trigonometric identity, you can write cosine A plus B, combination of sine and cosine, right? Or learn that trigonometry, right? So, but in terms of in the notation of complex function, then you can ignore all this trouble. Just write one thing in complex vector times this exponential function, and you take care of both the scientific aspect. Okay, so that's why I'm saying that using exponential expressions are much easier. You just need to follow the rule of working in complex functions, then the algebra will be much easier. Okay, so that's another way to say that the why we are using complex notation. Okay, but we need to figure out some rules. So one rule is how to take the product of two of these things. Now, J is like that. E is same, just like this. Minus -2 plus E complex conjugate. Okay, and then what you can do is now you just write out the product. So there will be 4 terms because you have 2 terms times 2 terms, so altogether 4 terms. Now you write it. This is the first is this times this J. Now we let ignore all the argument, all the argument, but just to say some right. J dot E is QI omega T. Right, and then this times that J dot E complex conjugate. Now this turns that is you have minus I omega T times E to the I omega T, so that cancels. So that becomes 1, right? And then so you don't have the exponential function here, and then this times that. Again, this is the same here. E I omega T, E minus I omega, that multiplied to 1, and then plus complex conjugate dot E complex conjugate into the 2I omega T. Okay, and now what we'll do is again obviously you're taking the real part, but by convention, all these are not just when you have a product term, you're not just taking the real part. You actually doing something like what we did in the last what we just did, the average over one period, and in that case, because you have 2 e to the this is double the frequency. When average over one period, all this cancel, all the goes to 0, right? And but these 2 terms doesn't have this exponential function anymore, so the average is just nothing. It basically it's just the same. And now these 2 terms are complex conjugate to each other, and you add the 2 and actually give you the 2 of the real part of either one of them. So you have 2 of the real part, and you divide it by 1/2, so it's 1/2 of the real part of one of this quantity. And by the usual convention, you're writing something. This real quantity equals to some complex thing. You're basically taking the real part, so you can say it's just 1/2 of J dot E complex conjugate. Or sometimes to be explicit, you can add the time average notation, but sometimes you don't do that. Just assuming that you're using the same thing, you're always taking the time average, right? No, you can use either one of them. So you can use this one or this one because yeah, taking the real part of this one or that one is the same. These 2 are just complex conjugate to each other. So basically when you have a product, everything is oscillating in the same single frequency. When you do that, you basically just multiply one thing and then another thing with a complex conjugate. I mean, in terms of this field that depends only on space, spatial coordinate, then one of them take a complex conjugate, either this one or that one. But the crucial thing is divided by 1/2. It's not just by, it's just not just J dot E becomes J dot E complex conjugate. Introduce a 1/2 factor. That's basically coming from the math. You have these two, and then you divide it by 1/4 each, because each one has a 1/2 factor, right? So that's what its 1/2 factor is coming out from this the product. Okay, so the first thing is this is more general than this discussion. Anytime you're discussing a physical system using a single frequency, and you have equation that depends on quadratic terms, and you use something like that, right? And to talk about the spatial dependency and get rid of this oscillatory thing. Okay, and then the rest is just to use this notation for the Poynting theorem. Okay, and the Poynting theorem will actually, instead of going back to the equation that I just talked about and substituting this into that, which is actually exactly the same, but we'll start it over. That's what Jackson did, because well, the J dot first, you have to already have the J dot E term. And we'll start from the J dot E term and then divide the Poynting theorem, right? But then you need the Maxwell equation to substitute into this the J dot E. So the Maxwell equation also change according to this single frequency. That's why I write it over here. Okay, so the only change in the Maxwell equation is that obviously divergence B is still 0. Divergence B is still 1. That doesn't change. Okay. Now Faraday's law is you have curl B is not curl. Faraday's law curl E is minus partial B partial T. And because of the single frequency, that expression, take a partial derivative with respect to T, pull out minus I omega factor. That is minus I omega T. And then the Ampere's law, you have curl H. Now you have the J term, which doesn't change. And then you have the partial D, partial T. Now that changes to plus I omega D. Right. Did I get it right? This is partial, yeah, actually minus. Actually this becomes plus. I actually take a derivative minus I omega T, then there's a minus, so that becomes plus, and that becomes plus. Okay, because originally it's partial D, partial T, but you pull out minus I omega, there's a minus sign, so minus I omega. Okay, now we have everything we have. So then you can use this two to substitute into the Poynting theorem. First is the J, right? You can use J to substitute into the work done, and then in somewhere along the line we'll do a divergence theorem, changing the volume integration to the surface integration. So we'll put that in the volume integration first. Over a certain volume. Okay, that so using this notation, one of just using just using this term, which doesn't matter. It's the same. Now you put back to J here. J is curl H. Now you take the complex conjugate, and then plus I omega d, but then you take the complex conjugate, the minus complex conjugate, and dot into E. And this one moves to the other side, become plus I omega d, but then you take the complex conjugate, you change the sign of I. Okay, so minus I omega d complex conjugate. Okay, and then now for this one you again use the vector identity that or in 6.7 we already looked at. Let's do it again. So basically, this becomes a divergence of. Let's look up the vector identity again. So divergence A cos B equals to C dot L A minus E dot B. Okay. And then finally, we want to write it as, for the convention is E cos H complex conjugate. We want to get this cos, this E cos B, so E cos H. So A is E, B is H, or H complex conjugate. Now you have, it's like here, A is E. So this one is like this one. So you, this is H complex conjugate. So you move this to the left-hand side, and which is now move this to the other side. So for the first term, let's you have the H complex conjugate dot into curl of E, and then minus this that what we want, divergence of E cos H. So that is this dot into this, using this one, return into this one minus this one, right? Yeah, that's right. And then plus or minus I. So it's just like what we did in 6.7. And this is what we call the Poynting vector, except that now we have the 1/2 factor and then the E cos H complex conjugate. Okay, and so this one combined with the 1/2, so S is now just using the same rule here. Just using the same rule, because originally it's E cos H, right? In the real quantity, it's just E cos H, but in terms of this notation, depends on all the spatial function only. You get this 1/2 of one of them times the complex conjugate of the other. So that is this term. Now for the curl E, you can use this one. This is just I omega B. So this is I omega times B. Right. So these two terms will be similar. So one is I omega H complex conjugate dot B. The other is minus I omega B complex conjugate dot E. Right. So now the final form is what Jackson did in 6134. So this one goes here. And you have for the Poynting vector, you can write it as now it's use the divergence theorem because it's total divergence, the divergence theorem over the surface of the volume, and S dot N dA. Okay, and now the other two terms you can multiply. I mean, take the I omega out. Right. Take the I omega out and combine the two terms. Right, I omega over 2, and then you have X dot B minus D dot E. So one is that the sign of these two terms are different. So that is one thing that is different from 6.7 because we're using this compact notation that will introduce this kind of sign difference. And one of them will define as WE. And now according to Jackson, we define WE, the electric field current energy density is 1/4 of dot B. And this 1/4 factor is coming from the same consideration, but the original the electric field energy density E dot D divided by 2, right? Remember that. In 6.7 we have that. The U, what we 6.106, the U, the field energy density is 1/2 of E dot D plus B dot H, right? So WE is like that, and WM, the magnetic field energy density. WM is 1/4 of H, B dot H. Complex conjugate. I mean, you can put complex conjugate on either one of them. This is just the way Jackson chose to write it. Okay, but then you realize that this when you put these two into here, one is plus sign, the other is negative sign. So this would be WM minus WE, right? And obviously, you need to multiply by 2. This 1/4. This is just 1/2. You need to come 2I omega divided by 4, and use the 1/4 go into here. This one WM minus WE, and finally you get Jackson's 6137 by putting everything on the on the left hand side. Okay, so write it out explicitly. J dot E. This is what we call the mechanical energy or the work done to the particles. And then you have when you move this to the other side, this becomes plus. So it's WE minus WM. And then this becomes plus the surface S dot E. everything going to zero. Okay, so that is the Poynting theorem in the single frequency configuration. Now the only thing different is this one. It's slightly different from what we had before. Remember the U is you add the two energy density of the two, right, in 6.7. But now when you use this complex machine, one is minus, the other is plus. The physical meaning is this field has this anti-correlation, this kind of they are out of phase basically. After you have the complex notation, this means you take care of the phase. They are out of phase, meaning that there's a transfer of energy from electric energy to magnetic energy and vice versa. So they are oscillating. Electric energy going to magnetic energy going to electric energy. So therefore, you have this one is positive sign, the other is minus sign, right? And then you have this. The rest is similar. You have the particle energy, and then the Poynting vector, right? And in this case, I think that's the end of the Poynting vector derivation of Poynting vector. The rest is divided like in circuit terms. If you learn about circuit, usually you use the current and then impedance, that kind of thing. This is just to write the whole thing in terms of that kind of language. But we won't have too many applications here. This is not a WE. When you are in WE class, probably will learn more about all these things. Right? But, so we won't go on to this one. But it's just coming from the Poynting theorem. Just identify different for a circuit. Identify which part corresponding to the instead of writing J dot E, usually we have I dot V, I times V. That is the power. That in circuit, usually I times V as power or the dissipation of power over the circuit. I dot E. You still remember your circuit or the circuit thing. And then you write down the resistance or the impedance, which has real part and imaginary part. So, okay, not going through that. Okay, but so that will stop in here for this section. Okay, any question up to here? Right. So for this section, the main thing that you learn about is how you express this product when you have this single frequency expression. And always remember this 1/2 factor, and how it comes from is from this process you introduce this 1/2 factor. Okay.